Welcome to this short demonstration. So here in this demonstration playground, and I really recommend you to play around with this at home, you see what I just explained on the slide deck before. So you see here, for example, we have two-dimensional input data, x1 and x2. We have two hidden layers in this neural network. So one hidden layer has 4 neurons, another hidden layer has 2 neurons. So for every neuron, what is happening, right? We get our input here. We multiply the input with the corresponding weight. So here you see the weight is 0.04 and here the weight is 0.27. These get weighted and summed up, and then this is the input to this neuron, and then the neuron applies a nonlinearity here, the sigmoid function, for example. And then the output of the neuron is passed to the next layer, right? You see here this edge goes to this neuron and this edge goes to this neuron, and again we have specific weights attached to it, however these values are weighted. Again, they're summed up here in a weighted fashion. We have this nonlinearity, the sigmoid, and then this becomes the output and so on and so forth. Okay, so this is the simple architecture. Again, you see here the weighting when you go with your mouse over it, and you can see here also the activation function in the upper part, right? And how this is then forwarded to the output. And finally, you see here also on the right hand side the data set we aim to classify, right? Class blue and class orange. And you see here in color the output of the neural network, which can be on the negative side, so then it's more orange, or on the positive side, then it's blue. And at the moment, with the current weights here, for example, right, however these were determined randomly, you see that it's all classified as orange. So this is not good. Okay. And this is now what you know already from machine learning, right? So this, of course, is not good, right? Because it's all classified orange. So we have a rather high loss, right? You see here the training loss is 0.5 and the test loss is also 0.5, right? And as a loss, we have used here for classification, of course, binary crest entropy. So what do we do at the end of the day? We want to find the parameters which minimize this loss, right? And what does parameters mean? In this case, it means the weights here, right? These weights and these weights, and here also these weights, which are the last from the logistic regression. These we have to find, and of course in the best way such that we have a small loss that most of the points are correctly classified. And this is indeed what you can do now in this playground. You can essentially now click on this button, and then we do, not surprisingly, gradient descent, and later on you will learn how to do this efficiently for neural networks, to do gradient descent on these parameters to minimize our training loss. And let me just click here on this, and you see that the training loss is going down, also the test loss is going down because it's a very simple data set. And now already you see that this looks much better. Again, this region is now classified as blue and this is orange, and we have a loss which is close to 0. So if we stop now, then you see, for example, here also in this playground, how the weight is now determined. So for example, here for this first neuron, this is not really important, as you see, right? Most of the weight is anyway very small. Here we have a larger weight, here we also, and here, for example, also as well, right? So for the simple data set, as you can imagine, this is linear separable. We can actually just apply logistic regression, right? Because as you know, logistic regression is essentially a neural network without any hidden layer. And if you train it now, you see, yes, it works, of course, right? Because this is enough to separate this data. However, if we, for example, go to a more complicated data set, like this one, this is not linear separable anymore. If we would now train it, right, we see the loss is still high, right? Because we cannot find a linear decision boundary between these two classes. This doesn't work. So what is then the hope? As discussed, we can, for example, add a few neurons, one layer, let's say, and then we can see whether this already is enough or not. So you see in this scenario, for this data set, apparently these four neurons, it seems to converge slowly, right? They might be enough, and yes, here it works, right? You see these 4 neurons are already enough to distinguish between these classes here. So what you can then do at home yourself, right? You can change the number of hidden layers, you can change the number of neurons you're using, you can change the complexity of the data set. Let's just play around here. So the spiral, so to say, it's rather complicated. So here with 2 layers, let's say we add a few more layers here, neurons here, so 2 layers, 4 neurons each. Let's see whether this works. So it might take a while because it's rather complicated, but the underlying principle is always the same, right? You see, we have different layers. Per layer, we have multiple neurons. We have multiple activation functions. So here in this demonstration, you can only pick one activation function, but in principle, you can use for every neuron a different activation function, for every layer a different activation function, whatever you think makes sense and whatever leads to a good performance. And you see here in this scenario, these two layers, for example, together with a sigmoid function are not good. If we, for example, take a ReLU, and let's say we take one more layer, let's see whether this works. So you see it tries to adapt, right? The region changes, but again, the spiral is rather complicated, of course, to classify. And then, of course, what you can always do, and this is not against like the idea of neural networks, of course, you can a priori also define some features. That's still possible, right? So you could say, okay, let me also now use x1 times x2 as an additional feature. Let's see whether this works better for this data set. Yeah, you see that this needs now to some different structure. Of course, you can still do some processing. So what we discussed is that neural networks can represent any function. But of course, if you have some kind of prior knowledge or if you have some other information, it's always also a good idea to have some predefined features if you know that they are helping for your task at hand, because then your neural network does not need to learn it. Okay, so whatever you know a priori, where you're sure about, so to say, that it helps, please try to define it, because learning everything might also not be a good idea. It might take a long time and you might need complex functions. So it might be a good idea to specify other aspects as well. And here you see already also some issue, right? It leads to a somewhat good loss, right? It also looks like that is potentially already overfitting, right? Because it has some crazy shapes, for example. So again, in general, please play around with this. You see here more or less all basic components of neural networks: your input, the layers, the neurons, the loss function, and the training procedure, how it works. But if you're familiar with the logistic regression optimization, what we discussed in the last videos, you can just again think about that this is just a more complicated function which we want to learn. So with this, I want to thank you for watching this very short video, and feel free to continue with the other videos, of course, as well. Bye-bye.